Let's deeply discuss the relational model. It is a way of organizing data using tables, right? This is the model used by MySQL, Oracle, SQL Server and etc. Right? First we should discuss about the relation, right? A relation is just a table with rows and columns, right? Example, student table, right? This whole table is equal to relation, right? Attributes, right? Attributes are the properties of the data, right? Example, student ID, student name, right? Just simply remember, attributes is equal to columns, right? Tuple is a single row of data, right? Example, this, right? I taught in the previous video that the relational model uses primary and foreign keys, right? What is the primary key? Uniquely identify each rows, right? Example, student ID. Normally we take IDs for the primary key as a result of IDs are unique from each other, right? The next one is foreign key. It links one table to another, right? Example, course table has a student ID. That is foreign key, right? You can see the student ID column in both of tables, right? See, student table has student ID as well as course table has student ID column, right? Therefore, we can also use student ID as the foreign key. According to that theory, student ID is we can get student ID as a foreign key and primary key, right? Tree schema architecture. This is a three-layer structure used in DBMS to separate how users see data, how designers see data, how the DB is stored internally. Think of it like three layers of a cake, right? First one is external schema. This is the top layer, right? And user view, right? This is the what user sees. Different users see different views, right? Hide unnecessary details. Examples, students see only their marks, lecturer see students' mark, all students' mark, admin sees everything, right? This is the user specific view of the database, right? Second layer is conceptual schema. This is the middle layer of tree schema architecture and logical view, right? This is the overall design of the entire database, right? Includes all entities, attributes, relationships, likewise, right? No storage details, one conceptual schema for the whole organization, right? Examples, student table, course table, enrollment relationship. The DB designers use this layer, right? Simply remember, it contains what designers plan, right? The last layer, internal schema, we can say bottom layer of tree schema architecture, right? It is physical view. This is how the DB is stored physically inside memory or disk, right? Like file formats, indexes, records, storage blocks, compression, right? Very technical, used by DBMS engineers, right? Simply remember how data is stored, right? Simply we can say how data is stored, right? What is the mapping? Mapping is the process of converting data requests and results between the three levels of the database management system, right? It helps the database management system understand what the user wants and how to get it from storage, right? First mapping, external conceptual mapping, right? Users make requests using their own external schema. It means their viewpoint, right? DBMS converts the user's request into the conceptual schema form, right? This ensures the system understands what data is being asked, right? In simple terms, use language converts into DBMS logical languages, right? Second one is conceptual internal mapping, right? The DBMS now converts the conceptual request into internal schema, right? Internal schema decides how data is physically stored, right? In simple terms, logical request converts into physical access path, right? Third one is this, right? When it returns data, internal conceptual do now physical data converted back to logical form, right? Conceptual extend do reformatted to match the user's view, right? In simple terms, physical data into large data into user-friendly data, right? Requirement collection and analysis. In this case, we talk to the user and understand what they want. It's like when customers come to our shop and we ask, what do you want, right? Document everything clearly. We used techniques like interviews, questionnaires, observation, and document analysis, right? We identify entities, attributes, relationships, business rules. In this case, the output is user requirement document, right? The goal is to remove conflicts and unclear requirements, right? What are the mistakes? Users often give incomplete or contradictory requirements, right? And designers must validate and refine them. Use cases to better understand data flows, right? Next one is logical design, right? Converts conceptual design into DBMS formats, right? Example, relational table, right? We can convert to ER into relational mapping, right? It creates table, columns, primary keys, foreign keys, and normalization, right? This is DBMS independent except for relational rules, right? The goal is to provide a database schema that DBMS can actually implement, right? Normalization removes redundancy. Denormalization sometimes used for faster queries, right? It includes mapping rules, right? These are the mapping rules, okay? The last one is physical design, right? It decides how the database will be physically stored on disk, right? It chooses indexes, file organization, partitioning, storage parameters, right? Focus on performance like fast queries, efficient storage, quick updates, right? Okay. The goal is to make the database run fast in real-world conditions, right? Chooses clustered indexes for frequently searched attributes. Use partitioning for every large table. Use materialized views to speed up real heavy applications, right? It considers block size, buffer size, RAID storage, access path, right? Simply remember, Physical design decides storage, indexes, file structure, right?